Hello, I'm Seema and welcome to part 23 of the chapter States of Matter. The topic of this video is liquefaction of gases. In the previous videos, when I explained the gas laws to you and I told you about the kinetic molecular theory of gases, this theory explained why substance or matter exists in the gaseous state. And what was the main thing about this theory which we realized was wrong when we talked about real gases? There were 2 points. One, that it had assumed that there are no forces of intermolecular interaction, attraction or repulsion between the molecules. And the second was that the volume of the molecules that they occupy is almost negligible in comparison to the volume of the entire gas. Now, gases, now we understand, they exist because the intermolecular forces of attraction and repulsion are almost negligible and the volume that they occupy is almost negligible. When does this happen? When the temperature is very high, the volume would expand. The pressure is very low. When you reduce the pressure, the volume is really large and you raise the temperature. That is when the molecules do not interact, the attractions do not come into play. And under those conditions, substances act as gases. But if we reverse these conditions and we start bringing the molecules closer and closer together, so close that their intermolecular forces of attraction, they come into play, they start working, they start attracting. And we start decreasing the temperature, which decreases the speed of the molecules, and therefore when two molecules are coming close to each other, they're so slow that the attraction becomes more important, or it becomes effective so much that it holds on to that molecule and keeps it there. That is when the gas turns into a liquid. So we can imagine liquids to actually be a continuation of the gaseous state. If the gaseous state is one extreme, the liquid state is just a continuation. It is the other extreme, but it's a continuation of the same state. And that is why liquids are usually called, you could imagine them as dense gases, and that's the reason why there is one common term used for liquids and the gaseous state, which is known as the fluid. They are called fluids or the fluid state. They are fluids. They flow, so they are fluids. So let us study about the liquefaction of gases. There was a scientist called Thomas Andrews. What did he do? He plotted isotherms of carbon dioxide. Now, I told you when I discussed Boyle's law what isotherms are. Isotherms are curves which we plot between the pressure and volume of a gas at a fixed temperature. So each of these lines that you see, each of these curves that you see are actually different isotherms. So an isotherm at one temperature, another isotherm, and what are we doing? At a particular temperature, we are plotting the curve along the volume and along the pressure. So we see at this temperature, if the pressure is this, the volume would be this. At this temperature, if the pressure is this, volume would be this, and so on. So that is how we plotted these different curves. So what did Andrews or Thomas Andrews observe about carbon dioxide? He noticed that if we take carbon dioxide at 50 degrees Celsius, where it is present very much as a gas, and we start compressing it, we start pushing the molecules together, like take it in a jar and have a piston and start pushing the piston downwards. So as we compress the molecules, press them together, what was observed? As you will press them together, what would happen to the pressure? The pressure would increase. So we find that as we compress, the volume decreases, but the pressure increases. And at 50 degrees Celsius, it very much follows the curve of Boyle's law, that is of an ideal gas. So carbon dioxide, as you compress it, it increases in pressure and the volume decreases and it gets the ideal gas curve. If we reduce the temperature and bring it down to 31.1 degrees Celsius. At 31.1 degrees Celsius, he started with the gas at, let us say, point F, and at point F the volume was V1. And now he started compressing it. as he compressed it, the volume kept decreasing and the pressure kept increasing until it reached G. And again, he found that he only had carbon dioxide gas. And the curve was still kind of following it was not exactly the ideal gas curve. There was a little deviation from that, but yet it was the gaseous state that he observed throughout. Now, when he brought down the temperature by just 0.02 degrees Celsius from this temperature, do you observe? The temperature here for the second line is 31.1 degrees Celsius. He now brought it down by 0.02. So it becomes now, the temperature becomes 30.98 degrees Celsius. At this temperature, a remarkable thing happened. As he was increasing the pressure and he was compressing the gas, the volume was decreasing. All of a sudden, at 73 bar pressure, he observed that all of a sudden the gas, that is the gaseous carbon dioxide, turned into a liquid. It was just a smooth transition. He did not observe anything. He just noticed all of a sudden as it came to 73, he was seeing the gas and it suddenly turned into a liquid. And now when he would increase the pressure further, with a steep rise in pressure, the volume did not change much. Like if the volume was Vc, when he brought it to, he compressed it further, it came down to V3. So for the gas, the compression was much more, but for the liquid state, the compression wasn't much, because liquids do not compress. But you should understand this, liquids do not get compressed much. So when it came to point E and we did it, the difference in the volume was not much. But the pressure, it showed a steep rise. Now there was one point worth noticing, that when he took the gas, that is carbon dioxide, at a temperature of just 0.02 degree, more than 30.98 degrees Celsius, he did not get the liquid state. He got the liquid state only at the temperature 30.98, and above this he would not get the liquid state, however much he might compress the gas. So he said this temperature is a particular temperature for carbon dioxide, and when he started trying it out for other gases, he found that every gas has its own fixed temperature above which it is only present as a gas, and that is the maximum temperature at which it can exist as a liquid. For carbon dioxide, this temperature was 30.98 degrees Celsius, and he called it the critical temperature. He said this is the critical temperature represented by Tc. And what was Tc, or critical temperature? Critical temperature could be defined as the highest temperature at which liquid carbon dioxide could exist. And above this temperature, that is above 30.98 degrees Celsius for carbon dioxide, even if it was just 0.02 degrees Celsius higher, you would not observe the liquid state. And for every gas has its own critical temperature. Just like every gas has its own melting point and boiling point, every gas has its own critical temperature, below which the liquid state is seen, above which it remains in the gaseous state. So now the temperature which was corresponding to, that is the critical temperature, whatever volume that substance had at that temperature was known as the critical volume. But volume of how much of the gas? Because if you take more gas, it would occupy more volume. So if we take 1 mole of the gas at its critical temperature, whatever volume it occupies was called the critical volume. So how do we define critical volume? Critical volume is the volume of 1 mole of a gas at its critical temperature, that is at Tc. Now the pressure corresponding to this, that is 73 bars, which I told you when the first liquid appeared. This pressure corresponding to the critical temperature was called the critical pressure. So how would you define critical pressure? Critical pressure is the pressure of the gas at its critical temperature. Now these three, that is the critical temperature, the critical volume and the critical pressure, These were known as the critical constants of a gas. And every gas has its own specific critical constants. Each one has its own critical temperature, its own critical volume, and its own critical pressure. Having understood this, now let us see Thomas Andrews did not stop here. He reduced the temperature of the gas, and now he again plotted the isotherm. He started compressing it. When he reduced the temperature from 32.98 to 21.5 degrees Celsius, and the gas was at A, he started compressing it. The volume was at A, let us say, and he started compressing it. He found that at point B, at a certain point B, he found that the liquid state appeared. The liquid state appeared not as it appeared at the critical temperature. At critical temperature, what had happened? All of a sudden, all the gas had turned into a liquid. But here he observes that there's a surface of a liquid that has come up, but it is not all of it. All of the gas that was taken has not turned into a liquid. So what did he observe? He observed that now, as he would go on compressing, you can imagine that there is a jar here and there's a piston, There's a piston in the jar. So as he is pushing the piston downwards, the volume goes on. Let us say he brought the piston down to this point. When he brought the piston down to this point, that much of volume decreased. And that volume that decreased will cause an increase in pressure of the gas. Isn't it? If you've studied that as you decrease volume, pressure increases according to Boyle's law. Because now a larger number of gaseous molecules are present in lesser volume, and therefore the number of bombardments of the walls of the container would increase. So what did he notice? When he compressed this gas below its critical temperature, and he's compressing it, you should expect an increase in pressure. But the pressure does not increase, rather the gas turns into a liquid. And not all of it, some of it. And how much of it do you think gets converted into a liquid? Those extra molecules which were going to contribute to the extra pressure, those many molecules will turn into liquid state. And therefore, the pressure remains the same, because those molecules which were now excess here, those many have been removed from the gaseous state. They have come into the liquid state. They have formed a surface, and now they are not participating in contributing to the pressure. So he observed that this line, as he keeps on compressing more and more, pushing the piston downwards more and more, the liquid state, more and more liquid state keeps appearing, and lesser gaseous state, in such a way that the pressure remains constant and the isotherm, it achieves a plateau. It comes to a plateau. The pressure is not increasing. It becomes constant. So we get a horizontal line. And then at point C, we find that at point C, where the volume was V2, all of a sudden now we do not have any more gas. All of it has turned into a liquid, that is liquid carbon dioxide. And now when he continues to compress it further, he finds that the volume reduces only from V2 to V3, but the pressure, it shows a steep rise. Why? Because liquids are not compressible. In very little even if you compress it a little, the pressure that increases is much, much higher. So we find this shows that liquids have very low compressibility. Then he reduced the temperature still further. Now he brought down the temperature to 13.1 degrees Celsius. This time he observed that the similar trend was observed, but this time this plateau, it became wider. It became wider. So you could imagine if you just join all these dots, that is, this is the point where the gaseous and the liquid state started coexisting, then the plateau came, and then at this point all of a sudden all of it turned into liquid, and now the liquid would have very little compressibility, and therefore it showed a steep rise in pressure on decreasing the volume. So this shows that there is a dome which is produced, which can be, if you join all the dots here from the critical temperature to these points which form the plateaus, we found that it formed a dome which I've made here. So if we take the gas at different temperatures between this, we would find it would fall into the dome, and as the temperature goes on decreasing, the plateau increases, the length of the plateau increases. So we can imagine now, or we can say that inside the dome there is an existence of two states, that is the liquid and gas, both of them are present. But inside the dome, the liquid state, you can see it separately as the surface of the liquid, and the gaseous molecules are, the liquid keeps settling down, the gaseous molecules are still there. So you have two phases and you can see them separately. But at this point now, all the gas is lost, it turns into liquid, all the molecules, they settle down to form liquid, and you have only the liquid, and then you increase. So this was about these were the different isotherms at different temperatures, and this is what he observed about carbon dioxide. And he said that all other gases also follow a similar pattern, and they have their own critical constants. Now, if we look at this entire graph, what do we observe? That A, if you look at point A, what is the physical state of carbon dioxide at A? It is the gaseous state. What is the physical state at F? It is the gaseous state. From F, if you take something to G, G also has the gaseous state. What is the physical state at E? At E, you have, if you just go here, it's a gas, and if you go here, it's a liquid. So at E, it is the liquid that appeared, only liquid. D has only liquid, because why? How do we come to D? It was temperature 21.5 degrees Celsius, that is below the critical temperature, and below the critical temperature gases liquefy. So this liquefied, it showed a plateau, turned into a liquid, and now when you're compressing, the red line is actually compression of a liquid. It is not a curve that is showing you compression of a gas. So D is a point where carbon dioxide is present as a liquid. H is also a point where carbon dioxide is present as a liquid. So this is what we observe about the various points and their physical states. And why have I pointed out these points to you? If we notice that when we carried out the compression at temperatures below the critical temperature, first of all, it is not possible to liquefy a gas above the critical temperature. This is something that we conclude from this graph, that if the temperature was above critical temperature, the gas will not liquefy, compress it as much as you want. But if the gas is at its critical temperature, then without touching the temperature, you can just push the molecules together to turn into a liquid at its other critical constants. And if the temperature of the gas is below the critical temperature, then it would follow this plateau form, and you would get a stage where you will have both the states, and then it would turn into a liquid, and liquefaction is possible. But now there's a question: is it possible to turn a gas into a liquid without going into this stage where you have a plateau? Is it possible to, or we say, is it possible to liquefy gases where in such a way that there is only one physical state present at a time? Instead of being inside the plateau where it is showing two physical states, that is the gaseous and the liquid state, is it possible to liquefy a gas where there is no presence of two or coexistence of two physical states? Is it possible to turn it from a gas all of a sudden to a liquid? Yes, it is possible. And let us see how that is done. So at 21.5 degrees Celsius, we take this gas and we compress. We would not like to compress it. Why would we not like to compress it? Because if we compress it now, it would come to B. And if it comes to B, it is going to enter the plateau. That is, it is going to start showing both gaseous and liquid states. And we don't want that. So what do? We first took carbon dioxide at point A of this volume, and now we increased its temperature. When we increase the temperature of A from 21.5 degrees Celsius to, let us say, 31.1 degrees Celsius, it comes up from A to F. It comes up from temperature A to F. Now carbon dioxide is present in the gaseous state at a higher temperature. So now if it is present at a higher temperature, what should I do? I do not want the gas to pass through the dome. If I want it to be in one state and turn into the liquid state, it should not enter the dome. So how will I follow the pattern? Now when I have F, I start compressing the gas at 31.1 degrees Celsius. It would stay gaseous and it would keep on compressing, and I'll reduce the volume so much that it comes down to G. Now when I reduce the volume so much that it has come down to G, I still have it in the gaseous state. How can now I need not compress it further. I've compressed it enough, but it is in the gaseous state, because we know that a gas does not turn into a liquid however much you may compress it above its critical temperature. And that's what we have done. We have really compressed it a lot, but it did not turn into a liquid because it was above its critical temperature. Now, when it was above the critical temperature, what had I done in the beginning? I had raised the temperature. Here, I would drop the temperature. The moment I drop the temperature, I start cooling the gas. As soon as I start cooling the gas at this volume, as soon as it comes to H, that is when it is going to suddenly turn into liquid. So without allowing the gas to pass through the dome by managing the conditions, the temperature, pressure and volume conditions, it is possible to convert a gas into a liquid without going through a stage where both the states exist. So this is what we understood about the liquefaction of gases. Now there is one more point that we can understand by looking at this graph. That if you had started this entire experiment not from 50 degrees Celsius but from 13.1 degrees Celsius, we would have observed the curves like this. So the wider part of the plateau, we would have made that curve first, and slowly the wideness of the plateau would have decreased and decreased till it reached one point. So critical temperature was that temperature at which the width of the dome, it became so small that it came and merged into one point. You can imagine it like that if we started with the gas at a lower temperature and the plateau was wide, we raised the temperature, made the isotherm, the plateau became narrower and then narrower until it came to the critical temperature at which the wideness of the dome, it narrows down so much that it comes and collapses into one point. That one point is the critical temperature, and corresponding to that you get the critical constants. At E, the horizontal curve merges to a point. And what do we conclude from our knowledge of this? From whatever we have studied, what do we conclude from this? We conclude that gases need to be compressed below their critical temperature. It is possible to turn a gas into a liquid simply by compression, but that is possible only if the gas is present below its critical temperature. If it's above the critical temperature, compress it as much as you want to, it would not turn into a liquid. So gases, they need to be compressed below the critical temperature to be liquefied. So there are some gases which are called permanent gases. I would refer you to the previous video, that is video number 22, where I plotted the value of Z, that is compressibility factor, versus P, pressure. And I told you in that graph, if you observed, hydrogen was a gas that showed continuous positive deviation. That is, it had at all pressures, it showed a value of Z greater than 1 or Z greater than 1. So such gases which always show a positive deviation are called permanent gases. So such permanent gases, they can also be turned into liquids by doing both the things that you can't turn them into liquids by just compression. You will have to compress them and bring the temperature down. So such permanent gases can only be liquefied by doing both the things, that is compressing them and reducing their temperature. Why? Because when you compress them, the molecules come closer. And when you reduce the temperature, the molecules lose energy. And when they lose energy, they don't run about from each other. They don't just brush past. They slow down. And when they slow down, that is when intermolecular interactions and attractions, they can work and hold the molecules and turn the substance into the liquid state. So, I just told you about the single phase liquefaction. There is one way. I just told you the long method of having a single phase liquefaction was to go from A to F to G to H and to D. The other way, which does not involve so many steps, would be very simple, that carry out the liquefaction at its critical temperature. If you had done it at the critical temperature, you would not go into the dome. You would be sitting at the tip of the dome, and all of a sudden the gas would turn into liquid at point E, or its critical volume and critical pressure. So this was about liquefaction of gases. Before I conclude this video, I would like to solve two problems that are given in the NCERT textbook. The first question, I'll just read it out for you. Gases possess characteristic critical temperatures which depend upon the magnitude of intermolecular forces between the gas particles. Critical temperatures of ammonia and carbon dioxide are 405.5 Kelvin and 304.10 Kelvin respectively. Now, the two critical temperatures have been given. Ammonia has a critical temperature of 405.5 Kelvin, while carbon dioxide has a critical temperature of 304.10 Kelvin. And the question is, which of these gases will liquefy first when you start cooling it from 500 Kelvin to their critical temperatures? Now, we are decreasing the temperature from 500 Kelvin. And as we decrease, which one will liquefy first? The one which has higher critical temperature will liquefy first. So we say ammonia has a higher critical temperature, therefore it will liquefy at 405.5 Kelvin, while you will have to reduce the temperature to 304.10 to liquefy carbon dioxide. So which one will liquefy first? Ammonia here would liquefy first. And then in the exercise, this is question 22 of your NCERT textbook exercise. Let me just read it. Critical temperature of carbon dioxide and methane are given. Carbon dioxide and methane. Carbon dioxide is 31.1 degrees Celsius. See, here the temperature was given in Kelvin and here the temperature is in Celsius. So it is 31.1 because when you immediately do it after that, you feel it's a different critical temperature. These are constants. It is always the same temperature. Only the scale is different. So carbon dioxide has a critical temperature of 31.1 degrees Celsius, while methane has a critical temperature of minus 81.9 degrees Celsius. Now the question is, which of these has stronger intermolecular forces and why? Remember, the molecules that have stronger intermolecular forces would liquefy first, because a liquid depends on that force. A gas depends on the forces of attraction to turn into a liquid. So the one which has a higher critical constant would be, or critical temperature, would be the one which would have stronger intermolecular forces, because that's the one which would turn into a liquid first. So in this case, we find it's a positive value. 31.1 degrees Celsius is much higher than minus 81.9 degrees Celsius. Therefore, carbon dioxide would turn into, would have stronger intermolecular forces of attraction. So these were just two problems based on the liquefaction of gases. And with that, we come to an end of this topic. And in the next video, I'll be telling you about the liquid state. And you could see the chart of critical constants. It's usually given in your book, or you could even during the exam, if you're asked a question, you would usually be given the critical constants. You're not expected to memorize them. So if you found the video helpful, please give it a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.